Welcome to The Explainer. Today we're diving into a study with a wildly long title, the Next Generation Benchmark Framework for Structural Control of Seismically Excited High-Rise Buildings. Yeah, it's quite a mouthful. But what we're really talking about here is absolutely fascinating. We're going to see exactly how civil engineers test out complex earthquake-proofing systems and how these very concepts are literally reshaping the safety of our cities.
So let's think about this incredible challenge for a second. Obviously, you can't just build a multi-million-dollar high-rise and then shake it until it collapses, right? That's definitely not going to work. But we also know that just relying on a building's inelastic deformation, basically letting it bend and break to absorb those severe dynamic loads, well, that's kind of outdated. Today, modern structural control uses passive, active, and semi-active devices to actually fight back and mitigate that damage. The real problem, though, proving that these advanced algorithms and hydraulic devices actually do what they're supposed to do before you put thousands of human lives inside the building.
Here is our roadmap for today. First, we'll look at the earthquake problem. Second, the standard testing ground. Third, the 20-story digital model. Fourth, the 3 modes of sway. Fifth, simulating damage. And finally, building a safer future. Let's get right into it.
Section 1. The earthquake problem and why we so desperately need better testing.
Think about it like this. Before this study came along, evaluating earthquake algorithms was honestly like trying to compare car safety ratings, but every single manufacturer is crashing their cars into a completely different type of wall. Over the last couple of decades, engineers have come up with some incredible algorithms and devices. But because researchers were testing their specific control systems on small-scale, isolated, or even totally proprietary models, there was zero common ground, no baseline. You literally couldn't tell if an active hydraulic system designed over in Japan was actually outperforming a semi-active damper designed in the US. You were comparing apples to oranges.
Which brings us to Section 2, the standard testing ground, or creating a universal framework.
The solution they came up with is essentially a digital crash test dummy. By creating a consensus-approved high-fidelity analytical model, suddenly researchers anywhere in the world can just plug in their own passive, active, or semi-active control strategies and see exactly how they stack up against everybody else. The absolute genius here is that the evaluation model itself remains totally invariant. It doesn't change. The only variable is the control strategy you're applying. It completely standardizes how we evaluate these sensors, devices, and algorithms. It's a total game changer.
Moving to Section 3, the 20-story digital model, also known as the LA benchmark structure. For this digital crash test dummy, the researchers didn't pick just any building. They selected a massive structure, standing right at 265 feet tall. That perfectly mimics the typical mid to high-rise buildings that completely dominate our modern city skylines today.
And to be clear, this is not just some generic imaginary box. This is a highly detailed, fully code-compliant building, originally designed by Brando and Johnston Associates for the SAC Phase 2 steel project. It's specifically tailored for the highly volatile seismic region of Los Angeles, California. We're talking 20 stories above ground, 2 basement levels, all held up by heavy-duty steel perimeter moment-resisting frames. When you add up the steel framing, the floor slabs, all the mechanical equipment, and the roof, the total seismic mass sits at 1.16 times 10 to the 7th kilograms. To put that massive number into perspective, that is roughly the weight of over 60 fully loaded 747 airplanes. Imagine all of that swaying at once.
Now, to make this simulation actually manageable to run in MATLAB without losing accuracy, the engineers had to be pretty clever. First, they mapped out 180 specific nodes right at the beam-to-column joints, and then connected them using 284 elements that represent the steel beams and columns. Originally, this created this unbelievably massive 540 degrees of freedom puzzle. But by applying something called a Guyan reduction, they were able to condense out the rotational and vertical degrees of freedom, the stuff that doesn't really dictate the building's overall dynamic response. So they boiled the whole thing down to 106 essential degrees of freedom, keeping the natural frequencies under 110 Hz.
Section 4. The 3 modes of sway and understanding the building's dynamics.
What's super cool is how the MATLAB simulation actually visualizes the invisible physics at play here. It breaks the building's sway into 3 distinct, really fascinating modes of motion. Mode 1 shows the whole building sliding uniformly over to one side. Mode 2 shows it kind of whipping or sliding right from the middle of its height. And then Mode 3 shows a highly complex movement where the building is actually sliding from 2 sides simultaneously. Understanding these foundational mode shapes is absolutely crucial, because that is exactly how engineers figure out where to place their sensors. For example, in their sample design, they knew exactly where to put accelerometers, on floors 5, 9, 13, 17, and up on the roof.
Section 5. Simulating earthquake damage, looking at the pre- versus post-earthquake conditions.
Because earthquakes aren't just one-and-done events, this framework forces researchers to test their algorithms on two totally different versions of the building, a pristine version and a damaged, worst-case scenario version. In the pre-earthquake model, the building is pristine. It actually has extra stiffness coming from non-structural elements like cladding and interior partitions, which boosts its natural frequency by 10%. But in the post-earthquake model, we assume all those elements have totally failed. Structural damage has occurred, leading to an 18.2% drop in natural frequency. Why does this matter? Well, if your shiny new algorithm only works on the pristine, undamaged building, it's going to completely fail during the inevitable aftershocks.
And to truly prove their worth, these control systems aren't just tested against random vibrations. They are subjected to the recorded seismic data of 4 of the most devastating historical earthquakes of the 20th century. Think of these as the ultimate boss battles for an engineering algorithm. The control inputs have to manage the actual chaotic ground accelerations recorded during El Centro in 1940, Hachinohe in 1968, Northridge in 1994, and Kobe in 1995. The researchers literally take the absolute horizontal acceleration and the interstory drift from those exact historical events and feed them right into the digital models. And they do this with an incredibly strict controller sampling time of 0.005 seconds. It is a rigorous test.
Which brings us to our final part, Section 6, Building a Safer Future and Achieving Global Resilience.
By giving researchers all over the globe a standardized, highly rigorous way to test and refine their algorithms, this benchmark serves as a massive catalyst for civil engineering innovation. As the paper points out, this coordinated effort enhances the potential for reducing structural damage and improving occupant safety, perfectly aligning with the overarching goal of building safer, more resilient cities worldwide. It just takes all the guesswork out of structural control. You no longer have to wonder if a new, semi-active shape memory alloy is actually better than a traditional hydraulic actuator. You just run them both through the exact same 20-story LA benchmark, throw the exact same 4 historical earthquakes at them, and the data tells you exactly what's going to protect the human occupants best. I really hope this exploration of the LA 20-story benchmark model leaves you as fascinated by the hidden world of structural control as I am. It is such a prime example of how highly complex mathematical modeling directly translates into safer physical realities for all of us. When engineers speak a common digital language, the sky truly is the limit for what we can build. But I want to leave you with this thought. If a shared digital framework can teach us exactly how to survive the most devastating earthquakes of the past, what impossible, gravity-defying structures will it allow us to safely build in the future? Keep asking questions, keep looking for the underlying structures in our world, and I'll catch you on the next explainer.